Okay, here's the first part of the 7-3 lecture. We may or may not get through all of it today. We'll do as best we can. It has to do with volumes. So we've gone from 7-1 looking at the integral as a way of notating a net change, and 7-2 to look at the integral as be able to figure out the areas between curves. Our next thing is to find the volumes of solids using integration. That's interesting. My calibration is off. Yep. All right. So here's the idea. First of all, I want you to think about, we have an object in 3 dimensions now. I will hold up my McCafe coffee cup. And of course, the most interesting thing about a cup is how much it holds. What's its volume? Okay? Now the question is, how can we use techniques of integration in order to find the volumes of solids, of objects? How much will this cup hold? How much will that can hold? All right? Here's the idea. In the previous section, we took a height, and we multiplied it by dx, which represented a width. And we represented that product as a drawing of a tall, skinny rectangle. And we said that the integration symbol then represented the sum of all of those products, the sum of all those little rectangular areas. This was a tiny bit of area, and the integral was the sum of all those tiny areas. Now, what do we do if we want to do volume? Well, let's take this particular very strangely shaped solid.
What is that?
It looks like a piece of a bone.
Yeah, but that was like the end of a cup.
I think if you take your instruction else.
It looks like one of the jellyfish that I saw at the Shed Aquarium last weekend.
Looks like weird jellyfish.
All right,
Melted gummy bear.
we'll use other more typical volumes later. But I want you to think about this particular cross section, the one where if I took my very sharp Ginsu knife and chopped through that solid, that solid, if I pulled it apart, would have a cross-sectional area. That shading area that I just said, it has area. Now, what if I multiplied it by its thickness? I would get the volume of just that one thin slice. If I took a area and multiplied it by a bit of thickness, this result is a bit of volume. Just one little bit of volume though. But what if I wanted all the little bits of volume? I'd add them up. So, whereas we would take something that represents a little bit of area and add them up for the area between the curves, we are now going to go to, I take an expression that represents a little bit of volume, and then I add up all those little bits of volume to make a big, to find out what the total volume is. So, let's talk about this in a particular, with a, well, you're going to think this is a strangely defined thing. There is actually, the definition of a cylinder is different than the definition that you grew up with. a cylinder, from the most general mathematical definition, is a shape in 2 dimensions, the same shape, and all of the volume in between it. You know it as a circle and another circle and all the volume in between it. But the more general definition in the mathematical realm is any shape the same shape and all the volume in between it.
Those are the same shape.
We're gonna blame the calibration. All right. So what we say is, if we knew what the area of this cross section was,
Why does it have x of k and then x of k minus 1? Wouldn't that just be 1?
oh, I know what the difference is. Okay, I'm sorry. I'm thinking that this shape was the same all the way through here. This thing is actually getting bigger. This green thing is the cross section at one side of this solid, and then this is the cross section on the other end. Okay, but what they would like you to do is, when we slice it, we get one single shape. All right?
So it's like a cut, because the bottom of the cup's not necessarily. Okay.
It's not straight all the way down. It like
Okay.
comes out.
And we slice it so thinly that it acts like a cylinder. It acts like a single little piece with a really little bit of thickness. And any cross-sectional area is being defined by that expression a sub x. What is the area of that cross-section for any particular x? It doesn't look like a sub x at all, does it? Try that again.
If you're adding them up, wouldn't they all be different?
Yes.
But how do you equate that they're all different?
Well, wait. When we did area between curves, wasn't the height of a typical rectangle vary as we went from place to place?
I don't know, I didn't watch that actually yet.
When we did the area under the curve, we did this one, y equal square root of x. Here's one rectangle, here's another rectangle, here's another rectangle. Those heights were changing based on where we were in x.
Oh, so you're just, okay.
So the width of each of these rectangles is being considered a slice of x, which we'll call dx. What we're saying in this new model is each slice of the solid gives us a cross-sectional area. That area may vary based on where on the x-axis we are. That's okay. We're going to take that cross-sectional area, which we call a sub x, and we're going to multiply it by a little bit of thickness called dx. Area times another dimension gives us a little bit of volume. Right? They're saying that if we broke it down into a finite number of slices, n slices, the amount of thickness would be the distance between x sub k and x sub k minus 1. Call that delta x. I'm going to bypass that. I'm going to say we're not going to break it into n slices. We're going to break it into an infinite number of slices. So we don't have a thick delta x slice of that volume. We have an infinitesimally thin slice of that solid. How thin? Dx thin. Leading us to the idea that the volume of the solid can be then equated as the integral from a to b of a sub x dx. I think we'd be better off doing something real as compared to talking about it theoretically.
Yep.
So we make it real? Okay, let's see what we can do. Ready for the next slide? All right. Okay, here's the basic technique that we're going to use for finding the volume using slices. We're going to sketch the solid, and then we're going to sketch a typical cross-section. For some value x, we're going to look for an expression that represents the cross-sectional area at x. We're then going to say, what are the limits of integration? Or what are the values that x are varying upon to make up that volume? And then we'll integrate that cross-sectional area, a sub x, dx, to find on those limits of integration in order to find the volume. Yes?
What do we do in the case of that first example that you showed, the cross-section, where it kind of starts out, it's almost like the cylinder you described, like the new definition we have now, but it kind of spread out almost, so.
Well, unless we have data like what those different cross-sections are, or unless we have a mathematical model that allows us to calculate what each of those cross, we really don't have the ability to calculate that volume. But it becomes a problem. Like, remember when in 7.1 where instead of giving the mathematical model of how things were changing, we were instead saying, here's the rate of change at this point, here's the rate of change at that point, here's the rate of change at that point. If we have that kind of information, we can still find out what it is using Riemann sum. But right now, I'm going to try to keep it from, we're going to be able to solve all of these analytically. Okay, so what we're going to do is we're going to find the volume of a pyramid. All right? So does everyone see a square-based pyramid here? You see it? Okay. And at some arbitrary point x, that pyramid has a cross-section which is indeed a square. Can we figure out for some value x what the area of that square is? Now let's try to make things a little bit easier. When x is equal to 3, this square is 3 by 3. What's the area when x is 3? 9. When x is 2, what do you think the area of the square is going to be? 4? Or if I said at some arbitrary value x, what do you think the area of that cross-sectional square is going to be? X squared. So if our general form for these answers, the volume is equal to a sub x dx, in this case, we think a sub x, a of x, is x squared. You give me a value for x, I can give you back the area of the cross-sectional square at that point. All right? Now, this again is an expression of area. But what happens when I take that expression of area and I multiply it by a little bit of thickness? This becomes an expression of volume. But just one little slice of volume. I don't want one little slice of volume. I want the sum of all those little slices of volume. So I want to integrate this. What's the smallest x value in my in this drawing? Way down there at 0. What's the largest x value that in this drawing of that square base pyramid? 3. So the volume of this particular pyramid is going to be the antiderivative of x squared, 1/3 x cubed, as evaluated from 0 to 3, or 1/3 3 cubed minus 0 cubed, or 27 divided by 3, or 9. And in this case, these are all meters, so this volume would be in meters cubed. By the way, does anyone know just what the volume of a pyramid formula is?
1/3 something.
Okay, well, watch this happen. Instead of going to 3, let's stop at some point A. The integral now becomes the integral from 0 to A of x squared dx. And I think you can pretty much see that it's going to end up becoming 1/3 A cubed at the end. So if A is the width of the square base, the volume of the pyramid is 1/3 A cubed. So you remembered the 1/3 part, right? Mm-hmm. Same thing with the cone. We'll be doing the cone later. All right, so again, we start taking slices. We find a description of the area of the slice, multiply it by dx, there's a little volume, add up all the little volumes. Are you ready for another try? Here we go. So here's a volume. Looks like a sideways vase, but you know, Edmund is seeing. It's a snack that smiles back. Yep. All right. So what do we have in this case? Well, this particular sideways vase is made by taking the curve 2 plus cosine x and twirling it around the x-axis. Like on a potter's wheel, it gets twirled, and this curve is marking the outside edge of that vase.
It's like a sideways wheel.
In this case, it would be like a sideways wheel, or if you can imagine picking this up and the potter's wheel turning in its. Okay, what do you call it? A lathe? A lathe could produce this object, and that's in the right orientation for a lathe, right? Yeah, you take a piece of wood or a piece of raw wood, it spins around, and then you can take a knife or you can take blades, and it will carve out portions, leave other portions. No, you're not. Anthony's like, I'll take your word for it. All right? So, this particular object is made by spinning that curve around that axis. Now, let's talk about a cross-sectional area for some particular arbitrary x. Well, what shape is that cross-section? A circle. So for some arbitrary x, I would like to know what the area of that circle is. What is a sub x? Well, go ahead.
What, 2 pi and whatever the f of x is?
2 pi? 2 pi?
Because 2 pi r for the circle.
2 pi r is not the area of a circle. That's the circumference of a circle.
Sorry.
What is it?
Pi
Pi r
r squared.
squared. Pi something squared. So I need to know what is the radius for that particular cross-section for some arbitrary x.
Except it's 2 plus x cosine.
2 plus x cosine x, quantity squared. So there we have it. That is a description of a cross-sectional area for that particular sideways vase. How do I change this into a volume? I integrate it. So volume is going to be the integral of pi 2 plus x cosine x squared times dx. Because remember, this is an expression of area, and when I multiply it by dx, I get an expression of volume. And that, of course, is going to add up all those little bits of volume. What are the limits of integration in this case? The smallest x value is -2. What about the largest x value? Is +2. Now, at this point, the majority of the work that we had to do is done. Actually integrating that, you know, this is going to be a monster because of this squared. You're going to end up using finite integral to find this value. Okay? Assuming that you know how to use finite integral in your calculator, I would like to go on to the next problem. All right? All right. How much we got? 9 minutes left? Okay. So here we go. This is probably going to be the last problem that we're going to do today. The region in the first quadrant enclosed by the x-axis and the graphs of y equal cosine x and y equals sine x is going to be revolved around the x-axis to form a solid. So let's do that first step, and that is, can we sketch what the solid looks like? Well, let me give you some hints about sketching these solids. First of all, let's sketch the region that's going to get revolved. It goes from, it is enclosed by the x-axis, y equal cosine x, which goes down like this, and y equals sine x, which goes up like this. So I'm only going to do this particular region, and I'm going to revolve it around the x-axis. Well, let me erase the parts of the curves that I don't need. So we start by drawing the region. By the way, where do they intersect? At what value does cosine and sine have the same value? Pi over what? 4. At pi over 2, cosine's all the way down to 0 and sine's all the way up to 1. It's the right triangle. The right isosceles triangle. All right? So here's the hints on drawing these solids. Once you draw the region that's going to get revolved, make a reflection of that region across the axis that you're rotating it. So it would look kind of like this. There's the reflection. Now, think about the parts that match up between the two. So someone said this looks like a bundt cake. It absolutely looks like a bundt cake. A sideways bundt cake. Typically a bundt cake would be like this. And you've got bundt cake, right? Bundt cake?
Yep. Yeah.
Bundt cake. B-U-N-D-T. Bundt cake.
Like in a pan.
Yeah. This is after you flip it out of the pan.
It's like
And the can itself,
Yeah, there's a,
Right. These are the dotted lines that you can't see.
you bake it.
It's a bun cake.
Oh, it has a hole in it.
Yes, it has a hole in the middle.
There's a hole in this cake.
So that's like the bunt cake, but that
Yeah.
way.
This is like here's the size of the cake.
And that hole is on this side. On the
The
right.
hole's here.
So much.
Okay. All right. Now, next step. Can we draw can we draw a typical cross section? So here's a typical cross section. It looks like a what?
Washer.
It looks like a washer. It doesn't look like a donut
Because a donut's three-dimensional.
because a donut's three-dimensional. A washer's three-dimensional, but its thickness is very, very thin. Well, I mean, the thing is with a donut is the edges are changing, where the edges of a washer are straight up and down. So this cross-section looks like a washer. Now what I want is the cross-sectional area of that washer. I want the cross-sectional area of that washer for some arbitrary value x. What I'm going to do, the cross-sectional area is going to be the area of the outside circle, which is pi r squared, and r goes all the way up to the cosine curve. Pi cosine squared, and that gives me the area of the outside of the circle. But now I got to subtract out the inside of the circle, which would be pi sine squared. So my cross-sectional area,
I don't get it.
okay, my cross-sectional area looks like that washer. That washer you're kind of looking at obliquely. This distance from the center of the washer out to there, this point is a point that's on the cosine curve. So the area of the big circle
It's going to be
is pi times this r squared, and that r squared is going to the cosine curve. Now, and then I'm going to subtract out the inside circle. The area of the inside circle is pi r squared, and sine is the radius of the small circle.
Okay, I'm
Okay.
having issues. I've been thinking about this entirely. What are you trying to achieve?
After I get this area function written, I can now integrate that area function with a tiny thickness dx, and when I do that integration, I get to find the volume of the bundt cake.
Is the entire first cake that you're talking
Yes.
about? Okay, cool. Because I was
Okay, remember the metaphor is when I was doing areas under the curve, while I was only drawing one rectangle, the integral represented the sum of the areas of all those rectangles. And while I'm drawing only one cross section, the volume of that one cross section, when I integrate it, I get all the little cross sections all added up, giving me one big volume.
So if you wanted to cut it and only use the bottom half,
Yeah.
would you still do it this way, but only go
But instead of integrating from 0 to pi over 4, I may only integrate from 0 to pi over 3.
to the point you cut it at?
That's
Okay.
the point I cut it at. So the 0 to pi over 4 determines how much of the bundt cake I'm calculating the volume of. Me, I'm doing the entire bundt cake because I love bundt cake. Chocolate with the white frosting. All right. So what do we get? The volume is equal to the integral from pi over 4, from 0 to pi over 4 of, let's factor that pi out. So I get just cosine squared x minus sine squared x. And unfortunately, you don't know how to integrate that.
Do you?
What?
Yeah, I do. I know a tricky trig identity that allows me to integrate it.
That we're gonna learn tomorrow.
It's called the power reducing formula. But what you do know is that no matter, since all these problems have limits of integration, you can use finite integral to at least get the numeric answer for that question.
Would you be able to use like vector?
Guess what? You bet.
I thought you were gonna say no.
No, I mean, almost always these kinds of volume and area problems that we're doing are almost always on the calculated portion of the free response section. By the way, the odds are 19 to 20 that you're going to get a volume/volume problem on your AP free response section. They're almost always there.